Okay, example 2. Let our production function be Q is equal to 9L to the power of half K to the power of half, where Q is equal to quantity produced, L is equal to labor, and K is equal to capital. So now we're going to calculate the marginal product of labor when L is equal to 100. Assume capital is fixed at 144. Okay, so at this point in calculus, if we are to look at the marginal product of labor, we need to have a fixed capital. We can only look at one variable changing at a time. So we're going to assume our entire problem is going to be based on capital being stuck at 144. Okay, so we're going to start by substituting that into our equation. So this is a condition, and when you're doing your work in the real world, you would make a note of that, saying a big assumption, capital fixed at 144. That would be a bold thing that you would put in to your assessment. Any assumptions like that. So this is 144 to the power of half, which is really the same as 12. It's the square root of 144. So I get 9 times 1 times 12, which gives me 108 L to the power of half. So this is the Q function when capital is fixed at 144. So now that I have a production function, I'm going to calculate the marginal product of labor. So MPL is the derivative of production Q with respect to labor. And it's going to be 108 times half L to the power of half minus 1, which is going to be really negative half. So this gives me 108 divided by 2, 54 L to the power of negative half. Or another way I could write it is 54 divided by L to the power of half due to the negative exponent. Now, the question is saying, what is this value when L is equal to 100? So my MPL, when L is equal to 100, is equal to 54 divided by 100 to the power of half, or the square root. 54 divided by 10 is equal to 5.4. That's your final answer. Okay, so what does that mean in words? That we would have an increase in production of 5.4 for an additional unit of labor, or one additional unit of labor. So if you increase labor by 1 unit, you expect production to go up by 5.4. Now, this has conditions. This is an incomplete statement. What is this dependent on? If capital is at 144 and also labor is at 100. This value is going to change if capital is different, and it will also change if labor is different, because this is a function of labor. So without this clause, this is a very incomplete statement. In fact, it can start to get dangerous because you need to note your assumptions. You need to note the conditions. Actually, that's not even an assumption. You need to note the conditions upon which this is true. And it's only true with the first clause. No complete marks without that. Okay, part B. Approximate the change in production when capital remains fixed at 144 units and labor increases from 100 to 103 units. Okay, so I'm going to expand on what Pearson presented, and I'm not sure I'm actually expanding on it versus just reiterating what Pearson presented. So when we get the derivative, MPL, it's really dQ over dL. Okay, now these D's are about infinitesimally small change. In math, we love to use D's to represent change. And in Greek, D is delta. And we use delta for bigger changes. Well, not big changes, still small changes, but not infinitesimally small change. So if we have change in quantity over change in labor, do you remember rise over run would be change in Y over change in X? This is called delta. And the D's here are just infinitesimally small changes. So what this does, it estimates that bigger change. It's not going to give you the exact change. If on a linear function, it'll give you the exact change. On a nonlinear function, it's not going to give you the exact change that you would get with 1 unit, but it's going to estimate that change. So if this is 1 unit, here's the real change. Let me make that bigger. Here's a function. Here's my slope line. So you could see over here, if I were to look at 1 unit of change, using that slope line, I would have a value up here. That would be the estimated change, whereas the real change is somewhere here. So it's not exact, but it gives a really good approximation. It's a very good estimate of what that change is. So using this relationship, if I want to estimate the change in quantity, it's going to be the change in labor, just multiplying both sides, it's approximately equal to the change in labor times dq over dl, or MPL. So if I want to estimate the change from 100 to 103 units, capital is fixed at 144. So I take the function. When capital is at 144, that's this. I do the derivative of it, that's this. I calculate it when it's at 100. That's this. That is that derivative that I need to do this estimate. So we've already come up with that value. So what I'm going to have here is the change in labor from 103 to 100 units. That's the change in labor based on dq dl at labor is equal to 100, which is 5.4. That's from part A. And that's going to give me 3 times 5.4, which is equal to 16.1. So that's my estimate for the change. Oh, sorry, 16.2. 16.2. That's my estimate for the change in production. That's right, Alex. 3 times 5.4. Now, if I was to compare that to what I would actually get, Q, when labor is equal to 100, if you put it in the actual function, you get 108 L to the power of half. What you would get is 1080. When labor would be equal to 103, this is our estimate that we just calculated. I'm looking at doing what's accurate, the actual change. And what I would get here for 103 would be 108 times 103 to the power of half. And that would give me 1096.08. The change in Q is equal to 16.1. So it's very close to our estimate using the derivative. Now this works more for small amounts of change as opposed to big amounts of change. You can see that if we were to talk about large amounts of change over here, we would lose accuracy. Can you guys see that? For large changes, we wouldn't use this approach, but for small changes, we would. Anybody have questions on that concept? Large versus small is somewhat relative. You are right. But it's just something to be mindful of and to recognize what percentage you're looking at of the applicable ranges. If Q only ranges between 0 and 2, where we're looking at 1 as 1 million, 2 as 2 million, then yeah, you wouldn't jump by a whole increment. You would be jumping at maybe tenths of increments. So change is what's large and small is very relative. Does the law of diminishing returns apply with this production function? Okay, how do I show that the law of diminishing returns applies with this production function? Well, the law of diminishing returns applies when a function has a curve like this. Because what you can see, this is my Q, and this is my either labor or capital. You can see that with this curve, your returns are decreasing and decreasing. So this is the law of diminishing returns. It applies when the shape is concave down. In other words, the second derivative has to be negative. So I'm going to prove that the law of diminishing returns applies by showing that the second derivative is negative. So I'm going to take my first derivative up here, and I'm going to take the second derivative. D squared Q over DL squared is going to be equal to the derivative with respect to L of the first derivative, 54L to the power of negative half. So this is going to give me 54 times negative half times L to the power of negative 3/2. So this is going to become negative 27 L to the power of negative 3/2, or negative 27 over L to the power of 3/2. Okay, now is this value going to be negative or is it going to be positive? How do we dissect that? Well, let's look at the denominator. The numerator is always negative. Can the denominator ever be negative? No, this denominator always has to be positive. L, labor, is always greater than 0. Therefore, L to the power of 3/2 would also always be greater than 0. The very nature of labor implies that this is always positive. Therefore, this is always going to be positive. Thus, this is always going to be negative. Over the range of values where the second derivative is negative, the law of diminishing returns applies. Questions on that? So for the law of diminishing returns to apply, you can see that it has to follow this shape that we have in this graph right here. And so this is a concave down shape. And this, you can only have the shape if the second derivative is negative. So we had to prove that the second derivative is always negative. It's very sad. It's very negative. The second derivative, because when we calculated the second derivative right here, the numerator is always negative and the denominator is always positive. Therefore, this is always a negative function. Therefore, the second derivative is consistently negative. The law of diminishing return applies over the full range of L values. Sometimes the law of diminishing returns only applies for certain production ranges over the range of L values where the second derivative is negative. But since this is happening everywhere, the law of diminishing returns applies for all from the get-go.